right, I guess we'll go ahead and get started. We got a little bit of stuff to cover today, and so we need to get moving on. And anybody who's late will have to catch up. All right, graphing sequences and series. Graphing sequences. Let me share this the other way because I know we're going to need to switch back and forth to Desmos. So it needs to be able to do that. Okay, the graphing sequences and series lesson. All right, so we're going to learn what key features are unique to graphs of sequences and series, and how can the average rate of change be found using a discrete graph. All right, so let's check out page 2. Okay, when we learned about arithmetic and geometric sequences and series, we learned how the domains have specific restrictions. Remember what we said about the restrictions on the domains? We said the range could be anything, right? Because our sequence of numbers has positive numbers, like we had 5, negative 15, positive 45. We can go either way, positive or negative. There's no restriction on the range. But as far as the domain, the x's, the first, the term numbers, we're restricted on term numbers. First of all, we don't have the 0th term. We don't have the negative 3rd term in our sequence. We don't have the negative 11th term. We don't have the 2.6th term of our sequence, right? Domain is restricted to counting numbers. Integers starting with 1. Integers greater than or equal to 1. So let's see. The domain is restricted to all integers greater than or equal to 1 because we don't have a 0th term of a sequence, or we don't have a fraction. We don't have a 3.5 term of a sequence. So can't even have a 0th place. So that's the restriction. But the range does have little to no restrictions at all, unless, let me say it this way. The range can have restrictions based on the situation. If we said that there's a farmer that has chickens, and every day he gets one more egg than he got the day before. So the first day he went out and got 2 eggs from his chickens. They weren't laying very much. The next day he got 3. The next day he got 4. It's arithmetic sequence, right? 2, 3, 4, 5, 6, 7. But the range is restricted in that case. There's no way that the farmer would ever go out and collect negative 5 eggs. Or he would never go out and collect 7.5 eggs. So in that case, we're restricted to numbers greater than or equal to 0. Because he could go out and collect 0 eggs. It turns out he didn't in that case. He started with 2. So it'd be 2 or greater. And would be restricted to only integers, only counting numbers, because of the situation. Arithmetic sequences in general could be anything, negative infinity to infinity. But you may have a certain situation that this is being applied to that restricts you just because. So you just have to think it. That's common sense. Okay, yeah, common sense. If he's collecting eggs, I'm not going to have a 7.681 in my range. It has to be a whole number. It has to be a positive number. So things to think about. Use your head when you got a problem like that. All right, we're going to learn a new term today that you may not have heard before. Discrete. Discrete. Now, I'm not talking about being very private with our formulas here and not letting people know what we're doing. That's a different kind of discrete, and that's spelled D-I-S-C-R-E-E-T. That's being discrete. Okay, now be discreet about this. No, this is C-R-E-T-E, spelled a little different, and this is a math term, and it means that something only exists at a certain value, like these sequences. If our sequence is 2, 4, 6, 8, 10, it's not continuous. It doesn't include 2.1 and 3 and 3.5 and 3.75 and 3. It only includes 2 and then jumps to 4 and then jumps to 6. That's called a discrete. Let's take a look at the graphs of discrete versus continuous. With continuous, we would make a line and we connect all of our points because we have a value at 2.5. At 2.5, it exists right there on the graph. It exists everywhere on the graph. But on a discrete graph, we'd only do the points. because there is no 2.5. There is no 3.3 term. It's only the third and the fourth term and the fifth term and the sixth term. So discrete. So we're dealing a lot with discrete when we're talking sequences. So in graphing a sequence, it's important to note where it'll show up. You may want to graph them by hand, but you can do it with Desmos. So let's use Desmos here, and I will show you 2 ways to graph a discrete function. And we will start with, let's say we're going to use this function right here. All right, the 3, 6, 12, 24, 48, 96. So we're going to graph that. And we know it has to be a discrete graph. We're not connecting these points. This is a geometric sequence, 3, 6, 12, 28. All right, so there's 2 ways. The first way is if you have all the values, you can say, okay, I'm going to make a table. And the first term is 3, and the second term is 6, and the third term is 12, and the fourth term is 24, and the fifth term is 48, and the sixth term is 96. So look at that. It graphed a discrete graph. See that? If I keep zooming out, I'll get all, there's the 48. And that makes a nice discrete graph. It's like, wonderful. Look at that. Does it all for me. But what if I'm graphing 15 terms of a sequence and I don't want to have to calculate all 15 and make a table? Can Desmos do that for me? Actually, it can. All right, let's look at just a arithmetic sequence. And if we look at this arithmetic sequence and we come up with a formula for it, let's see, what did I do with my pencil? Well, I went over there. Let's say we have this arithmetic sequence that is just 1, 2, very simple, right? 1, 2, 3, 4, 5. So if we made a formula for that, it's just y equals x in this case, right? Because the first term would be 1, 1. Second term, 2, 2. If we make it a table, it'd be 3, 3, because the first term is 1, second term is 2. So this is the simplest, right? We just make a y equals x. And I want to graph that on Desmos as a sequence, not the line. But if I say, okay, f of x equals x, that would be the continuous graph. But I'm going to turn that off. I don't want that. Now I'm going to say n equals, and I put this bracket. So now it said, oh, you're making a list. You're making a list. I say, okay. And it goes from 1, comma, dot, 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 all the way to capital N. All right, that's when I don't know how many terms. If I know how many terms, let's say I'm going to do the first 15 terms, or 20 terms. So 1 to 20. I'm graphing from 1 to 20. The first 20 terms. I put 3 dots in between those two just to show that there's a bunch of numbers between there. And said, this is what I want you to graph. The first term, right? Comma, I'm just putting a point on there. F of x. Or did I do that right? Let's see. 20. It says I made a mistake there. Too many variables. I don't know what to do with this. I just did this yesterday. Is it capital N? No, it's N, comma, f of x. If I did N2, it's that. If I do f of x, oh, it's not f of x, it's f of n. F of n. N and f of n, which means take whatever term it is and substitute it in for x. So if I graph this point, the point n f of n, it'll take my 20 different n's, 1 through 20, as the x value of my point, and the y value would be substituting that 1 through 20 into my equation. And look, there is the first 20 in that arithmetic sequence. Very nice. I didn't have to calculate what all 20 were. It's like, well, it'd be easy with this, but what if it's 1/2 x minus 6? All right. Well, there's the first 20 terms. I didn't have to calculate what the first 20 terms were and make a table. What if it's geometric? Let's put in a geometric one where we just use our geometric formula for a geometric sequence. I'll go back and show you what the formula was because this is from our last lesson. The geometric sequence. A1 times r to the n minus 1. So let's start with the sequence. Let's see. We had 1, 4, 16, 64. So that would be 1. So I don't need that. We just need r to the n minus 1. So let's do that. So if we said it's 1 times r to the parentheses x minus 1. Oh, not r. The r was 4. Here's that geometric sequence. Starts with 1, goes to 4. The third term is 16. The fourth term is 64. So you can see all the terms. And we did the first 20. So if we keep zooming out, there's going to be a lot more numbers way up higher. They get big really quick. The seventh term is 4,096. It gets big really fast. But we can zoom back in here. So we can do that on Desmos. Put the formula of your either arithmetic sequence or geometric sequence. Choose the number of terms you want, 1 through 20, 1 through 8, whatever it is. And then put these points. Now notice I turned this one off. That's the continuous. I turned that off. I said, don't graph that one for me because I don't need the continuous. Just graph the point. And you can turn the points on and off too, but see. So you want to turn the points on. Graph the point n, which means first term, and then f of n, whatever the first term calculates to be. N is 2, the second term calculates to be. So it just graphs those points. And you can have it labeled them for you. Just click that little label button, and there's your points. First term is 1, second term is 4, third term is 16. So Desmos very nicely can graph arithmetic and geometric sequences for us. 464. Oh, that's nice. All right, average rate of change. Let's talk about the average rate of change. So you may have a problem. Okay, let me be honest. You will have a problem. We won't say may. That gives you a sequence. Let's just use the one we graphed just now. 1, 4, 16, 64. And it may say, find average rate of change between x equals 2 and x equals 4. You will have problems like this. I know there's problems like this. It'll be on the test. It'll be on the assignment this week. Find the average rate of change. Okay, so what's that asking for? It's just asking for the slope between the second point and the fourth point. If we looked at it in a graph, it's like it wants to know the slope between 2, 4, and 4. If we connected those 2 points with a straight line, what would the slope be? For 2, 4, and 464. So we have a formula for that. It goes way back to Algebra 1. Our slope formula, where you subtract the 2 y values and divide them by the subtraction of the 2 x values. What are the y values? Well, when x equals 4, 1, 2, 3, 4, 64. That's y2. Minus y1. When x equals 2, 1, 2, that's what the y equals. We can look at it in our graph if we're confused that. Well, here's When x equals 4, the y value is 64. When x equals 2, the y value is 4. So we can look at it on the graph, or we can look at it on the sequence, 1, 2, 3, 4. Divided by x2, well, we said that was 4. It told us what the x's are, and x is 2. So 64 minus 4 is 60. 4 minus 2 is 2. So the average rate of change is 30 between x equals 2 and x equals 4. That's not the average rate of change between x equals 3 and 4, because that's a lot steeper here. I'm going to change how this displays it to make it a little easier. So if we say this goes from negative 10 to positive 10. Take all those little minor things out of there. Kind of spread those out a bit. See, the slope between 2 and 4 is not as steep as 3 and 4. 3 and 4 is steeper. If we turn it on, we can see that. See, it gets steeper as it goes. So if we calculated, I'll do this. If we calculate between 3 and 4, between 64 minus 16 and 4 minus 3, 64 minus 16 is 48 over 1. So the slope between x equals 3 and x equals 4 is 48. That's a lot steeper. So in a geometric sequence, the rate of change is going to be different between the 2 points, between any 2 points. With an arithmetic sequence, it should be the same because you're adding the same amount every time. The slope is consistent. The slope is consistent with arithmetic. But the average rate of change is going to be different in a geometric sequence depending on the 2 points you choose. So I guess this should be in your notes if you don't remember it from Algebra 1. How do I find the slope or average rate of change? Average rate of change equals slope. There we go. Put that there. That equals the slope. That is an O. This is the same thing. Average rate of change equals slope. So if you don't have that formula memorized, you need that in your notes when you get to that average rate of change problem that we're going to have. All right, let's go back. Average rate of change. There's that formula, m equals y2 minus y1 over x2 minus x1. So they have some examples there that you can look at in our lesson. All right, so he shows how to graph an arithmetic sequence, and he does it by hand. We've already looked at it in Desmos, so I'm not going to watch this video, but you can watch the video if you need to, if you want to go back and see that. But we've done that on Desmos, showing you how to do that right up here. All right. Explicit arithmetic sequence, and this is showing how to graph this arithmetic sequence, which you could put that into Desmos. So what he did is he took A1 plus DN minus 1 and substituted. He got 3 replies for his birthday on the first day. He got 5 more the second day. So the second day he got 8 replies. Then he got 13 replies, and he got 18 replies. And you can just put this formula. You don't have to simplify it. They simplify. You can put it just like this, and it would graph it. So let's see. 3 plus 5 n minus 1. 3 plus 5, and we do x minus 1 since it's on Desmos. And there it is. He got 3 replies to his birthday the first day, then 8, then 13, then 18, then 23, then 28. Just put in the arithmetic sequence formula and let Desmos graph it. See, there's their graph. Looks just like our graph. All right, and geometric, same thing. Just put the formula in, and it will graph it. This one's the one that goes down. It's a decay. All right, so page 4 has our summary. There's the 2 formulas again that you should already have in your notes with more examples. But the lesson summary just talks about graphing, restrictions to the range and domain. Remember, domain is greater or equal to 1. Notice when it graphs it, not the equation here, It starts at 1. It doesn't graph anything at 0 or the negatives. Desmos knows that when you graph a sequence like this, you have to start at 1 because we told it we're limited to 1 to 8. Because we know that we're limited starting at 1. We can't have a 0th term. So Desmos just graphs what we tell it. All right. The graphs are discrete, meaning they're not connected. They're not continuous because it's only valid at specific points. There's the formulas for graphing sequences, graphing series, and the average rate of change formula. So let's look at the lesson that goes with the assignment that goes with this lesson. Oh, look at there. The very first one, calculate the average rate of change. The rate of change. Another average rate of change. This one's arithmetic. This one's geometric. Graph the first 6 terms. They give you the first term and the common difference. So you can do that on Desmos and compare, or you can look at this to see if that is actually correct. The first thing I would say is you know what the very first term should be. A1 equals 3. A1 equals 3. So you should be able to do that without graphing on Desmos because this one says the first term is -10. Starts at -10. It can't be right because you know the first term is 3. So that should give you a big hit right away, which graphs you can eliminate because it doesn't have the first term as 3. -10. That's just silly. Here's another one. First term is 2. The ratio is 4, so it goes up times 4 every time. So what do they have? That's a little harder to tell if it's at 2 or not, but they give you the points right here. 1, 2, 2, 8. So they give you the points. All right, graph the 6 terms of a finite sequence where A1 is 5 and the ratio is 1.25. So which one of those graphs would do that? It uses that ratio. It goes up by 1.25 each time, starts at 5. All right, that's it. Just 5 problems, and most of them are matching the graph to the problem there. That's all we have for this week. Go forth and complete algebra. And I should have all the grades updated for your grade check today. So see ya.